Rotational dynamics. Just like there were rotational analogs for kinematics, there are rotational analogs for dynamics. Kinematics allowed us to solve for the motion of objects given initial conditions, but we didn't care why or how they moved. Dynamics showed how the application of forces. Dynamics is all about forces and how they cause motion. These are summed up in Newton's 3 laws. These laws also apply to rotational motion, but will be in a slightly different format. Forces underlie translational dynamics. A new term related to force is the foundation of rotational motion. It is called torque. Here we have a wrench, this object here, and here's a nut. We're going to apply a force at point A in the down direction. Don't look at this picture yet. Consider the axis of rotation of the nut to be through its center. So here's the axis of rotation right through the middle of the nut. The nut will turn or rotate in a clockwise direction, just like you can see that red arrow there. Okay? Recall that left and right really have no meaning when you're talking about circles. You have to talk clockwise or counterclockwise. Now this is good. A force is causing a motion from rest, which implies an acceleration. But it's an angular acceleration this time, so it's a little new. Let's take another case. Let's apply the force. We don't have a wrench this time. We're just pulling down on the nut at this position here. Here's the axis of rotation coming out of the board. The nut is attached to a bolt that is stuck into the wall, so it won't move down. Will the bolt and the nut rotate if we apply a force right here at the axis of rotation? As we just said, the nut will not rotate or move at all. It makes sense that the nut won't move translationally, as the friction of the bolt and the wood holding it is providing an equal opposite force. But why isn't it rotating? It rotated when we applied a force here, but is not rotating when we apply a force right in the middle. Let's assume we're using the same magnitude of force at points A and B. What's the difference between these two cases? Why is it not rotating now? The difference is the distance between where the force was applied and where the axis of rotation was. When the force was applied at the axis of rotation, the nut did not move. So just keep that in mind for a second. We'll come back to that. There's just one more variable to consider for torque. Here's a picture of a door. Right here, this is the door. Okay. Here's the door hinge right there. It's very conceptual. And you want to push the door. You want to open the door. Okay. So you have two choices. You can push it perpendicular like this, or you can push it at an angle. Okay. You can be pushing it from this side or pulling it from this side. The force vector is the same. Which force will cause the door to open quicker? In other words, which will have a greater angular acceleration? You've probably known this since you first started walking, whether you're a year or 2 or 3 years old, whatever. Pushing perpendicular to the door, or F1, gives you the greatest angular acceleration. So you guys have actually been doing physics for a long time. It will also allow a smaller force to have the same impact as a greater force applied at an angle different from 90. So if you can do a force F2, and that will open the door, and we'll show a little bit later that if you didn't push it at that angle but pushed it 90 degrees, you could use a much smaller force to get the same result. So there's something here about the perpendicular nature of the force which gives you a greater torque. The combination of the force applied, and let's look at F2 here this time. Combination of the force applied and the angle that the force makes with a line connecting where the force is applied to the axis of rotation, and how far away you are from that, is all combined to form torque. and we represent torque by the Greek letter tau, and it's equal to R times F times the sine of this angle. Torque is a vector. However, the above equation shows the magnitude of the torque, and that's what we're going to be working with. The direction of the torque is going to be coming in or out of the page, and we don't have to worry about that just yet. But we will talk about if the torque causes an object to rotate in a counterclockwise direction, the torque will be positive. Negative values of torque will cause clockwise rotations. We're trying to stay consistent with our definitions for omega. The sine theta part of this equation takes into account that the closer your force is applied perpendicular to the line, here's the line that connects where your force is applied, connects it to the axis of rotation. The closer your force is to here, the perpendicular, the greater your torque will be. Theta is the angle between the applied force and this line. So you can see that if both of these F's are the same, you use the same force, the torque due to this force is going to be RF sine theta. R is the same for both of these forces, but the sine of an angle less than 90 is smaller than 1. When I take the torque due to this force, that angle is 90 degrees. The sine of 90 is 1. So the same exact force applied at the same point on the door, which is the example we've been using, you will get a greater torque with F1. It is closer, well actually in this case F1 is actually on the perpendicular line. When you get to vector calculus someday, this equation becomes much more elegant and involves something called the cross product, where the torque, and now we're using the full vector form, is the distance here R, cross, and distance again in a vector form, cross F, which is the force. And that works out to be, when you're dealing with magnitudes, just RF sine theta. The units of torque are Newton meters, and you can see that. Sine theta is unitless, F is a force, that's newtons, and R is in meters. Note how this is similar to work and energy, and in those cases, we replace Newton meters with joules, named after James Joule. Torque, however, is a vector. How is this different from work and energy? Take a second. Okay, that's a second. And here we go. Work and energy are scalars. So to emphasize this difference, torque is never expressed in terms of joules. We will always just use Newton meters.